Hi, I'm Solomon Waneri, a lecturer in the Department of Biomedical Engineering, Faculty of Engineering, University of Lagos. Today we'll be looking at analog to digital converters. Lesson objectives are to describe the function of an analog to digital converter. Explain the steps for implementing analog to digital conversion. Design a simplified sample and hold circuit. State and explain the Nyquist theorem. Analog to digital converters. Analog to digital converters translate analog real-world signals like temperature, pressure, voltage, or current into a digital representation of the signals. You know, most of the real-world signals that we interact with are analog in nature. When you want to measure temperature, your body temperature is usually in analog form. Or you want to measure voltages, they are analog signals. So real-world signals are analog signals. They have to be converted to digital signals for your microprocessor in your equipment to be able to interpret these signals, because your microprocessor is a digital device. Your microprocessor is a digital IC, and for it to be able to understand the analog signals that is obtained from the physical environment, those analog signals need to be converted to digital signals. That is the purpose of analog to digital conversion. So this digital representation can then be processed, manipulated, computed, transmitted, or stored. An analog to digital converter samples an analog waveform at uniform time intervals and assigns a digital value to each sample. So that is basically what happens. The analog to digital converter samples your analog waveforms, meaning that it takes those analog waveforms at specific time intervals. It records those analog waveforms at specific time intervals. The digital value appears in the converter's output after it has been converted to digital signals. Most signals, as I said earlier on, in the real world are analog signals. These signals need to be converted to digital signals before sending it to the microprocessor to enable the microprocessor read, understand, and manipulate the data. One of the major benefits of analog to digital converters is high data acquisition rates. The data acquisition rate of most analog to digital converters are usually very high. With the invention of a wide variety of analog to digital integrated circuits, data acquisition from various sensors becomes more accurate and faster. So analog to digital converter is an electronic integrated circuit that is used to convert the analog signals such as voltage to digital signals, which are usually in binary forms like ones and zero. Note that an analog to digital converter is usually in the form of an IC, an integrated circuit. Most of the analog to digital converters take a voltage input as 0 to 10 or -5 to 5 voltage. They measure voltage within those ranges and correspondingly produce digital output in the form of binary numbers. The following steps are often used in implementing analog to digital conversion. The first is sampling of the signal. The signal has to be sampled. The next is quantization. After the signal has been sampled, it has to be quantized. Then finally, digital encoding of the quantized signal, or what we call encoding, is what takes place, which produces the digital signal. So let's look at each of these steps. Before that, sampling. This sampling has to do with taking records of the analog signals at specific time intervals. Taking records of the analog signals at specific time interval. The sampling rate is the number of samples that are measured or taken per second. It determines how fast the analog to digital converter is able to do the conversion from analog to digital. Usually, the time interval between samples is called the sampling interval. The sampling interval. And the formula for sampling interval is usually the inverse of the sampling frequency. The inverse of the sampling frequency, that is 1 over sampling frequency. Let's look at Nyquist theorem. The Nyquist theorem states that a signal with the bandwidth B can be completely reconstructed if 2B samples per second are measured. What it simply means is that the sampling rate should be greater than twice the highest frequency to prevent what we call signal aliasing. The sampling rate should always be twice the maximum frequency to prevent signal aliasing. So the sampling rate is usually greater than 2 times the maximum frequency of the samples. When aliasing takes place, it's simply the effect of overlapping frequency components. And what happens during signal aliasing is that it's difficult to reconstruct the signal to get the exact signals that were initially taken, because signal aliasing modifies the signals from what they originally is. Let's look at some worked examples. The first example, a signal was found to be made of constituent frequencies 900 Hz, 1800 Hz, and 2400 Hz. Assuming that this information was collected accurately, what was the minimum sample rate required to find this information? So let's solve it. The minimum sample rate is the Nyquist rate, which is twice the maximum frequency contained within the signal. And based on what we have been given, we have 3 frequencies: 900 Hz, 1800 Hz, and 2400 Hz. So the maximum frequency of the 3 is 2400 Hz. So to get the Nyquist rate is simply 2 times the maximum frequency. That is 2 times 2400 Hz, which gives us 4800 Hz. The next question, question 2. If a 120 Hz sinusoidal signal is sampled at the rate of 160 Hz, what will be the alias frequency? The alias frequency component is equal to the sampling frequency minus the message signal, which is equal to the sampling frequency, which is 160 Hz, minus the sinusoidal signal, which is 120 Hz. So the difference between them gives us 40 Hz. That is the aliased frequency. Question 3. Calculate the Nyquist sampling interval for the signal C into 600T plus sine C into 800T. First, we should know that 600t, based on the standard calculation, is equal to omega t. 600t is equal to omega t. 800t is equal to omega t. And omega is equal to 2 pi f. Omega is equal to 2 pi f. So what simply means is that 600t is equal to 2 pi f. For the first one, 2 pi f1 is equal to 600 pi. Therefore, f1 is equal to 600 pi divided by 2 pi. The pi cancels. So the answer is equal to 300. For the second frequency, 800t is equal to 2 pi f2, which is equal to 800 pi divided by 2 pi, which gives us 400. So the maximum frequency of these two frequencies is 400. So the sampling frequency, Fs, is 2 times the maximum frequency, which is equal to 2 times 400 Hz, which gives us 800 Hz. Now we know that the sampling time interval, or the sampling time period, is equal to the inverse of the sampling frequency. And we've already gotten the sampling frequency to be 800 Hz. Therefore, the sampling time period is equal to 1 divided by 800, which gives us 0.00125 seconds. Let's look at the simplified sample and hold circuit. The simplified sample and hold circuit describes how a circuit for implementing sampling. What happens is that this circuit has two operational amplifiers. It allows an analog input to enter the first operational amplifier. And once the circuit is still open, there is a switch. There is a switch that is open. When the switch gets closed, sampling takes place. Sampling of the signal takes place. And when the switch opens, the signal is held. So that is why we call it sample and hold circuit. And usually the output is still an analog signal, because at the stage of sampling, the output is still an analog signal. The next stage after sampling of signal is quantization of sample signal. Quantization is the process of taking a continuous voltage signal and mapping it to a discrete number of voltage signals. So what happens during quantization is that after the signal has been sampled, meaning that the record of the signals have been measured at specific points, those points are now joined to give us discrete time intervals. So quantization makes the range of a signal discrete so that the quantized signal takes on only a discrete value or a discrete set of values or finite values. Thus, it converts a continuous amplitude sample into a discrete value. You know that a continuous value can have any range, but a discrete value has specific values at specific time intervals. The number of voltage levels affects the quantized noise that occurs. So since digital computers are binary in nature, the number of quantization levels is usually a power of 2. That is, the number of quantization level n is equal to 2 raised to power small n, where small n is the number of quantization bits. This is signal quantization. The blue line, at the point of the blue line, the signal was sampled. Then these red lines are showing you that the signal are now quantized. You can see that they are in steps. So after this 0.01 01 value. It goes to the next value, which is 0110. They are now quantized. 0111. They are discrete values now instead of continuous values. Then the third stage is signal encoding. Encoding is the process of converting the quantized signals into a digital representation. This encoding is performed by giving each quantization level a distinct binary value. So what happens in encoding is simply giving each quantized level a discrete value, usually binary numbers. Now, the analog signal has now been converted to binary numbers, which we call analog to digital conversion. So for instance, if 4 bits are used, the lowest level will be 0000, and the next will be 0001. So what happens during encoding is that the quantized values are now converted to binary values, which are digital values. So you can see that the analog values, which could be a form of voltage like 5 volts, have now been converted to digital values, which are binary numbers. So that is what happens in analog to digital conversion. Here are some of the references I use. You can also consult them for further reading. Thank you for watching.